So good afternoon. My name is Lucy Nu. I'm a software performance engineer from Intel Corporation. So today I'm going to talk about how to accelerate Spark for genome sequencing in the cloud. As we all know, the industry trend for Spark deployment is really going from on-premises to the cloud deployment for many, many good reasons. First, the cloud deployment is very easy to do. You don't need to purchase your own hardware. All you need to do is to decide on one cloud service provider, determine what you want and how much you want. Then hopefully the deploy button will take you to where you want to be. Secondly, the cloud deployment is very easy to maintain and manage. Imagine a case, you have a failing hardware disk or your kernel is just crashed. Many features from the cloud service provider will take care of this for you. You don't need to wake up in the middle of the night, rush into your production center to solve the trouble, right? So it's very easy. Then most importantly, so the cloud deployment give you the elastic resource partitioning between the compute to your data to your storage, networking, and memory. So when you, on the on-premise side of the world, when you purchase your hardware, the ratio between the compute to network to I/O is already pretty much determined. When your workload behavior changed or you want to do something else, it's very hard to change the ratio unless you have some additional money to purchase extra hardware. On the other hand, the cloud deployment is very easy for you to make elastic choice from application to application. Whenever you change the behavior, you just tell the cloud service provider what I want and how much I want. With all this said, I'm still going to be very fair. The cloud deployment is not flawless. It has its own disadvantage as well. So first, there might be some limitations on the performance counters with the cloud environment versus the on-premises. You gain the manageability at the expense of lose the full control, right? So nothing is really, really free. And at the same time, please do not expect the exact performance directly moving from the on-premises to the cloud without any reprofiling or retuning your workload. Then the goal of this presentation really is we would like to introduce a data-driven approach to work around these limitations and by the end of the day to speed up your Spark performance in the cloud. The first question and the most complicated question people ask is, well, now I have these cloud deployment choices, right? So should I have one instance with 20 cores and a network attached storage, or I should go with 10 instances with 2 core each instance and locally attached storage? By the end of the day, I would think this is the same computation power. Are they the same? If not, which one is better? Well, the answer to the first question is no, they are not the same. And to the second question, it really depends. It depends on the behavior of your workload, and also it depends on how you partition your resource, the ratio, the balance bar you slide between your compute to your network, to your storage, to your memory, based on the workload behavior, right? So, and here is a very quick example, a very simple example. And I give you a bag of money. You deploy this Spark application in the cloud. So the first thing I would do is, let's just start from the 36 cores with 9 storage disks. It's a very simple configuration, right? Then later I found out, oh, wait, I see a big chunk of my CPU cycles is waiting for I/O to complete. There's a lot of waiting happening. My computation resource is just wasted. How about I reduce like 2/3 of my computation power, since I'm waiting anyway, right? So to 12. Then I still keep the exact same number of storage disks. Now I say, great, my CPU is fully utilized to 100%. And I achieved about similar performance. Look, I saved 2/3 of my computation power by achieving the very similar performance. Is that it? Anything else you can do? Let's wait till we see the configuration number 3. Let's edit a little bit computation power on the CPU side. Let's do 15 cores with exact same storage configuration. Now, I see my CPU is fully utilized, and my disk is also fully utilized. I get about 15–20% better performance than the case number 2. This way, I make sure I fully utilized everything I could in the cloud environment. I squeezed every single bit performance I can squeeze from my investment. That is the end goal of every single company, right? So the conclusion here is the resource partitioning is really your key to the success. You should really pay attention to the ratio. Where you are on this balance bar, you want to shift to the left or you want to shift to the right. Okay, so I know it is very important, but how? How can I know where I am, right? So I don't even know if there is a case number 3 existing. Maybe when I'm done with case number 2, I know, I already think I did a good job, the end of the story. So people are more common to recognize they are overutilized the resource because you may see a lot of waste, you may see a lot of like latencies on your hard disk when you found out there's the I/O takes too long to return. But people are not very common to realize you are underutilized the resource. You don't want to waste anything. Here we are introduce an approach, a data-driven one. Here we use at Intel on the performance work we do day in, day out. So we normally the starting point is a baseline. In this case, let's start from the on-premises environment. Then as the first step, we profile the Spark application and the Java virtual machine. The information we want to get out of this stage is if there is any locking contention issues between the threads. How about the Java garbage collection? So is there any non-pause or anything we can do there? Or is there any hot functions? What is the percentage of your hot functions? Maybe there's anything we can do to make it like run better. So that is the goal for this stage. Then after that, let's profiling at the system level. We want to get the utilization of the CPU, of course, first of all. Then we want to get the utilization of your I/O, including network and the storage as well, to make sure we are right on the middle of this balance bar. The most important thing we want to emphasize here again is the resource repartitioning in the cloud. Okay, so any questions so far before we jump into a case study, the work we have done together with Broad Institute of MIT and Harvard on this genome sequencing work? Any questions from the audience? Okay. So over last year, we have collaborated with Broad Institute of MIT and Harvard on Accelerate Spark for genome sequencing. The workload we use is this Genome Analysis Toolkit, GATK, which is a structured programming framework designed to enable fast development of efficient tools for next generation DNA sequencers. It is an industry standard, and also a lot of people collaborate and contribute to the project. If you guys are interested in, this is open source, 100% open source on GitHub. So please feel free to check it out. Okay, so for the rest of the presentation, we will just follow the approach we already discussed. And we do the data profiling into each of the 2 categories, then see how far we can stretch the performance out of it. So the first thing we do is to profile the application and the Java VM itself. The tool we use is called the Java Flat Recorder. It is shipping with Oracle JDK. So it offers the exact information on what we want. It offers the thread knocking contention information with the call stack. It also offers the hot functions with very detailed call graph, and as well as the garbage collection. It also offers compilation and other information, but due to the length of this presentation, we will be focusing on the 3 things we listed here. Any questions? Okay. So the first example we want to give is a knock contention example. So from the tool, the Java Flat Recorder, we found out there is Spark uses this synchronized map a lot in many, many applications. Then when we use that, especially with the multi-core system, there's a heavy contention happened with the, when we see like more than 50% of our CPU cycles is waiting on this single knock. Then what can we do about it, right? So we replace it with the concurrent hash map. Then the knock is just released. Then all the CPU cycles translate into very useful user time. Then the performance of the target stage is kind of improved by 3.5x. So this is just an example on what kind of information you can get from the data profiling and how the tool can help you to improve your performance. The second example I'm going to give here is with the exact same tool, we identified another Scala scalability issue. The issue happens inside the Scala APIs. So Spark, a lot of Spark code is written in Scala, right? So which is caused by concurrent calls from the Java instance of operator. So a lot of people here in the audience are Java coders, like me too. So sometimes, maybe a lot of times, we use this instance of, right? But until we use the tool, we didn't realize this instance of has this big of a scalability issue. Then when you increase the number of the thread count inside the JVM, the issue is getting worse and worse. So how can we fix it? And we did a lot of researches. There are multiple ways to fix it. The current approach we took is to use the polymorphism way instead of the instance of operator. Then just by applying this polymorphism way, we see about 60% performance improvements in the critical stage, which is the instance of happening, the most of the instance calls happening, and 30% improvement across the entire workload. The code changes we contributed is already being released with Scala 2.12.0 version. So if you happen to run into the same issue, just upgrade your Scala version. It might help you. Or please use this tool. Use this tool today. It may help you to discover other contentions, other hot functions you may not know before. Then it will help your performance. Right? So if you want if you want detailed information on this optimization, please go to the link here. So it has all the performance numbers and the performance claims about the details on the issues. It's listed there. Okay, so since instance of is really like a JVM thing, it's not only happen to Spark. So this issue is like a fundamental issue of JVM. So whenever a Java application is using this instance of, you will facing the exact same issue. As an example, we already found this happens in Cassandra. We used the exact same approach to solve it. And we found out the performance improvement is quite amazing as well. 61% better throughput and 15% reduction in the 99 percentile latency. 99 percentile latency is really the focusing area, right? So nobody is really care about the average latency. Big companies is always care about 95%, 99%. That's the area you want to improve. You want all your customers to be satisfied, not the average number of customers to be satisfied. So, yeah, then the number 3 example I want to give here is on the garbage collection. So using the exact same tool again, the Java flat recorder, we record the whole workload running, the measurements, then we got the data. One of the hottest functions from the garbage collection is this copy to survivor space function. That is the name of the function. Then that is actually 7 or 8% of the total cycles spent on the system, which is a lot to us. Then what does that mean, right? So when an object is created on the heap, it will first be created on the hidden space. Then when doing the minor GC, it will be moved to one of the 2 survivor spaces. Which one is free? It will be moved there, right? So then, and the object is possible to be bounced back and forth between the 2 survivor spaces. And eventually, if it is really, really non-living project, it will be moved to the old generation, just matured there. Then this copy to survivor space really means is the object being copied from the hidden space to one of the survivor space and being copied between the survivor spaces. Then how can we do about it? There are 3 parameters we can tune about GC. So again, on GC, this is another very, very big topic about Java, right? So here we only cover very high-level information. So one is the survival ratio. Survival ratio is the ratio on size between the hidden space and the 2 survivor spaces. How can you do the sliding? Again, resource partition between the size. Everywhere is about this partitioning. And the other 2 threshold is kind of like a group. One is the initial tenuring threshold. The other is the maximum tenuring threshold. These 2 thresholds is to decide when this object will be finally moved to the old generation. In our case, we did the tenuring distribution check. We found out majority of our objects are pretty non-living. So eventually, majority of them are moved to the old generation. Eventually, then we thought in order to avoid this kind of copy to survivor space function calls, maybe we just make it tenuring faster. We don't need to back and forth since we will be there no matter how. Then after this tuning, we gained about 10% performance just because of this garbage collection tuning. Again, without this tool to tell us this hot function, we are clueless. We don't know how to tune. If you look at the website from Oracle, the tuning parameters only for garbage collection, there are like tens of them. And there are a lot of combinations you can do. There are a lot of values you can tune. So without the tool to tell you where are your hotspot, it's very, very hard for you to decide. This just like save your effort for tuning, make you direct toward your target. Any questions? Before we move to the second category of the profiling. Okay. So the second category of the profiling is to profile the system. So you need to understand the utilization of your CPU, of your memory, of your I/O before you make any detailed decisions, right? So the tool we use here is called PAT, PAT, Performance Analysis Tools. I didn't put the information here, but it is also a GitHub, an open source project. If you are interested, please let me know after the presentation. I can give you a link to the software. Try it out. So the information we get tells us, and the baseline shows up to 40% of the CPU cycles spent waiting on I/O. So I/O is a big topic, right? So then with the same number of cores, we keep the computation the same. We just partition the sliding bars. We're changing the cores to storage ratio from 32 to 1 to 4 to 1. Just by doing that, we get 40% better performance out of the exact same workload. So again, so this just highlights the importance of this resource partitioning. By understanding the behavior of your workload, maybe in this case it's the I/O. In your own case, maybe you are memory bound. Maybe you are compute bound. Everybody has a different workload. Everybody has a different usage model. So understand your workload, understand your application. Do the proper partitioning to your resource is your key to the success. Any questions? Okay. So to summarize the presentation, Spark deployment is really moving from the on-premises to the cloud. Cloud environments provides many, many advantages. The most important one is the elasticity. But at the same time, this brings up the challenge for all the companies to properly repartitioning your resource. Profiling applications and understand the behavior of your workload really can lead to a good performance improvement. So before we conclude the talk, I would like to acknowledge my colleagues who are not here today, but contribute a lot to the work here. So we work as a team, and we deliver big. Thank you. So if you have any questions, please feel free to contact me or my co-presenters. I have the contact information listed here. Thank you. Thank you for your time.
Okay, if there are no questions, it looks like there are.
Oh.
Hi, was there any particular hardware setup that you had to do for the Java flight recorder? And also, can you share your GitHub?
Yes, definitely. So for the GitHub link to the tool, so please talk to me after the presentation. I can write it down for you very quickly. And talking about the configuration, all the work we have done is with Intel Xeon server, so codename Haswell. So that is for our on-premises work, and for the cloud work, we use Google Cloud. Any other questions?
Hi, can you explain your reason for choosing the flight recorder as a sample application? Because it's not built for distributed computing, and you were trying to use Spark, and it's really built for like a vertical machine.
Yeah, of course. So, and to get the hot functions and knocking contentions, you can use many, many other tools. The reason we choose flat recorder is first, it comes with the Oracle JDK, which you don't need to do anything extra. You can get the same information from perf, I believe, but for the Java applications, the tricky thing is the symbol file. So you need to use other tools and like APIs to get the symbol file translated into the name of the functions. So, but with the Java flat recorder, it is already done for you. So, which makes the case much easier. And Spark is written in Java, so that also gives you like all the information together, including the application itself, which is from the GATK or from the Spark, Scala, and together with the JVM information, including the garbage collection, as well as the compilation. So it's like an all-in-one bundle. So that's the reason we choose to use Flight Recorder.